Hello everyone and welcome to my talk. My name is Jonathan Sheavly and I'll be discussing the simulation-driven design of chemoresponsive liquid crystal sensors by tuning analyte partitioning. First, I wanted to discuss some of the motivation for using sensors and therefore talk about some of the health effects of pollution. So pollution can exist in many forms. We can have water pollution, soil contamination, or air pollution. And specifically under air pollution, we can have CO, ozone, SO2, and NOx, which fall into the general category of small molecule analytes. And these can have a variety of health consequences, such as headache and fatigue, respiratory illness, and cardiovascular illness. So in order to prevent people from getting some of these health effects, we'd like to be able to recommend places to avoid. However, the problem with recommending places to avoid is that these is a map of the current ozone sensors within the United States. This may seem like a lot, but if we zoom into this small area right here and look into the scope of a city, specifically New York City, we only see 4 of these sensor stations. And the reason why that is that these sensor stations are actually these giant air monitoring stations which are the size of buildings. And even with current state-of-the-art technologies, you can kind of get to the point where you can put one into your hand, but this is not convenient enough to get widespread data in order to recommend areas to avoid. So we need to design some new sensors with the objective of being portable, cheap, and selective. And our proposed solution is a liquid crystal sensor. So before I go too much into the sensors, I wanted to discuss some background into liquid crystals. So liquid crystals are a state of matter that exhibits short-range translational degrees of freedom, resembling a liquid, and long-range orientational ordering, resembling a crystal. Now, these collective orientation of the mesogens, shown here, or the liquid crystal forming molecules themselves, describes a director vector, shown here as N, which tells you the average orientation of the mesogens within the nematic liquid crystal. Now, when you put these into a sensor, what happens is the analyte, shown here in pink, approaches the surface through the mesogens when they're a homeotropic configuration here. And once they reach the surface, they displace a homeotropic mesogen and create a planar mesogen that's only pointing in a different direction. As this planar mesogen is displaced, then this reaction is then propagated vertically and it can be observed optically. And how that works is the homeotropic regions shown by the directors here and this image here do not rotate light in a cross polarizer, which means they appear dark. However, with the planar configuration as shown in this cartoon, light is allowed to pass through the cross polarizer because it does rotate light. So meaning going from homeotropic to planar, we see a brightness change. So some of the key design challenges for the sensors include the ability to predict the sensor response time. And what this means is if we measure the normalized optical intensity versus the exposure time, we observe the transition moving from 0 to 1 after a certain amount of time. So previous DFT calculations, which only measure the difference between the analyte bound state and the mesogen bound state, can predict the response time from that binding free energy. And this is valid for a reaction limited case. However, we would like to be able to understand what is the role of transport through the film when the reactions are fast. So in order to measure the role of transport, we use atomistic simulations. So we model the 5Cb mesogen using both a united atom and an atomistic model, and we first validate the measurements using glutaraldehyde, methane, and DMMP, because those values exist in the literature. And then we also measure the transport properties of all of the analytes of interest. And the systems for which we use to verify these and measure the transport properties is we use a vapor-liquid crystal interface. Then we use a bulk liquid crystal where we're using periodic boundary conditions, which simulates the 18 microns of liquid crystal that exists between the air interface and the substrate. And then we use this system to predict the role of transport. So what we first need to do is parameterize these mesogens. So by fitting torsional potentials between these middle two biphenyl rings to a quantum mechanical model, so this GAF plus fit, we were able to obtain a new parameterization for our atomistic model. Secondly, what we ended up doing was refitting the partial charges in order to better map to the electrostatic interactions and the electrostatic potential field near the mesogens. So the result is, once we transform from this united atom model, which is used commonly in the literature, and the all atom model, what we see is that for our P2 order parameter, when we compare to experiments at our temperature here, while we don't observe the same nematic isotropic transition temperature, we obtain similar P2 order parameters at the temperature of interest. Also, while we may not get the correct density across the entire temperature spectrum, and neither does the united atom model, we do get the correct density at 300 Kelvin. Additionally, when we measure the diffusivity, the united atom model overpredicts the diffusivity of the mesogens by an order of magnitude. And since we want to measure transport coefficients, inaccuracies in the diffusivity can be quite problematic. Whereas for our atomistic simulations, our diffusivities are fairly comparable to that in experiments. So this builds an extra bit of confidence in our model. Now, we first wanted to validate our model using experiments. And experiments can measure Henry's law coefficients, which can predict partitioning. We can compute Henry's law coefficients into solvation free energies using the following equation. What we can do in simulations is we can measure these delta G solve here from alchemical free energy calculations. And that's a free energy calculation which predicts the free energy moving this vapor phase analyte into this 5Cb phase. The simulations then, looking at this plot, show a very good agreement with the experiments. So if we use the AA model, which is what we're using in the remainder of this work, the agreement with the experiments definitely follows the correct trends and looks even better than the previously used united atom model, being more chemically specific. The first thing we did was then measure the solvation-free energies for the analytes of interest. So for these analytes of interest, we measure the total solvation-free energy shown in the blue columns. For the most analytes, partitioning is driven by electrostatic interactions. This is especially true for water and ozone. So we wanted to understand why this was the case, so we measured the coordination to the cyano group. So this radial distribution function, which is the probability of finding an analyte an r distance away from the cyano group, is extremely peaked for water and ozone. So those were the ones that had very strong electrostatic interactions, and not nearly as peaked for NO2, which showed very weak electrostatic interactions. This correlation shows that these electrostatic interactions stem from interactions with the cyano group. Now, what we can also do is look at the influence of the interface on the transport in the film. So what we can do is we can define the permeability from the inhomogeneous solution diffusion equation, where we have 1 over the permeability is equal to this integral involving the potential mean force, which is the free energy projected onto the reaction coordinate, in this case z, divided by the diffusion coefficient. So in simulations, we can measure this potential mean force for water, chlorine, and SO2 as an example, and in comparison with their bulk values, and we can measure the diffusivity as a function of this distance from the interface and compare them to their bulk values. And then what we can do is we can also define the bulk phase permeability, which is simply defined as if we treat the PMF and the diffusion coefficient constant and perform this integral and rearrange. So these fluctuations in this PMF are very strongly correlated to these density fluctuations which occur within the system. This is why we hypothesize that there would be some potential barriers in the system of the permeability. Now, once we actually compare the permeabilities for the interface and the bulk, what we see here for water, chlorine, and ozone is that the interfacial permeability is orders of magnitude greater than the bulk permeability. This means that the analyte travels much faster through the interface than it does the bulk, meaning that we can neglect the interface and the interface does not present a barrier for activation. So now we can measure the role of transport through the entire film all the way down by only focusing on the bulk liquid crystal measurements. So if we do that, we can actually quantify the amount of time because we developed this fast reaction model, which predicts the activation timescale from transport limited system. So we found that the timescale is proportional to 1 over the interfacial mass transfer coefficient plus the thickness divided by the permeance, which the permeance is just the permeability divided by delta. So since this is just a proportionality, we can't exactly put that on a plot, but what we can do is we can compare it to the timescale relative to another analyte in the literature, which we have a lot of literature on DMMP. So we can measure this timescale relative to DMMP, and that's exactly what we plotted in this figure over to the right. We have our model shown here in the master curve in the red, and then we have points in the blue, which are where our analytes fall on that curve. So the model predicts many of these atmospheric pollutants are actually along this regime right here, where the activation time is strongly dependent on the permeance. Additionally, in order to suggest more design possibilities, we computed the dependence on the thickness by doing an rate order analysis similar to what is done in catalysis and kinetics. We can then plot the dependence on the log of the time versus the log of the delta, and what we can find is for analytes like chlorine, we see a quadratic dependence. However, for DMMP, we show a very linear dependence on the activation time based on the thickness. So this means that for analytes such as chlorine and NO2, we can suggest changing the thickness and having a very large effect on the actual activation time, whereas changing the thickness will not have nearly as large an effect on the activation time for DMMP. Now, once we measure these characteristics and transport coefficients for 5CB, we can make some recommendations on using a different liquid crystal, and specifically our experimental collaborators recommended TL205. And so this is a 50-50 mixture of these two mesogens, and by incorporating these into our atomistic model, we can achieve bulk nematic phases. So then what we can do is directly jump into the transport of these analytes within TL205. So we can measure the permeance for each of these analytes in both the 5CB and TL205 system, and what we see is, in general, is a decrease in the permeance for all of the analytes that we have observed. And the greatest difference exists for water, where we see an order of magnitude decrease in the permeance. So this has the effect of increasing water tolerance. Water tolerance is an extremely important and desirable feature because water is everywhere and we don't want it to interfere with the signal. Also, analytes with similar permeances in 5CB, such as NO2 and H2O, and CO2 and SO2, are now stratified. So this predicts that TL205 will be more selective for these specific analytes, and they will be better for identifying the difference between these analytes. And in conclusion, what we found is that transport properties, such as the partition coefficient and the diffusion coefficient, can be predicted from MD simulations. These properties can predict activation time in liquid crystal sensors, and by predicting activation times, we can evaluate sensor selectivity between analytes. And by changing the liquid crystal leads to deviations in activation times towards different analytes. And what this really means is that MD simulations can select liquid crystals which change the selectivity and the tolerance towards targeted analytes. Also, in the future, we will use some of these exact same methods to predict the effects of additives on the liquid crystal film transport. And with that, I'd like to acknowledge my group, including my advisor, Reed Van Lane, as well as the other graduate students and postdoc in our group. These grad students are also presenting at AICHE this year, so I invite you to check out their presentations. I'd also like to thank some of my collaborators in this project, including the Zavala group, the Mavrakakis group, and the Averitt group at Cornell, and also, along with that, my funding sources. Thank you very much, and I'd be happy to take any of your questions on the Zoom chat.